Quantum computing is transforming business and science. It promises precise, side effect-free medicines in biotech, better batteries, smarter materials, new sources of alpha in finance, and breakthroughs in climate research. Who knows? Maybe even a tiny step towards saving the climate and world peace if it helps us solve global challenges together.
World peace? Really? Let's stay grounded. Quantum computing can solve certain problems more efficiently on paper, but the machines we need for large-scale algorithms are still far away. Real versions of Shor's or Grover's algorithm need thousands of stable qubits running for hours or days. Today we have a few hundred qubits with coherence times in milliseconds at best. So fully quantum algorithms are not arriving this decade.
Sure, but we do not need perfect machines to explore hybrid approaches. Shallow circuits, smart feature encodings, and classical optimization already let us build real models and test them on practical data. And in some early finance experiments, hybrid models have shown small but real gains compared to classical baselines.
And what about barren plateaus in quantum circuits? And is quantum really adding any bottom-line value to machine learning? Some say a quantum layer inside an AI model is just decoration, not a real improvement.
And this brings us to the point of the video, classical versus hybrid. A clean and honest comparison. Let's find out whether a quantum layer can add value in a classical machine learning model. Welcome to video 12. After our last finance video on QML, where we introduced a pure variational quantum classifier for credit card fraud detection, we now build a classifier for S&P 500 market regimes to establish the battle of classical versus hybrid. Our goal is not to maximize prediction performance, but to compare capabilities on the same task. Accuracy, F1 score, and per-class recall. This is an experiment about fairness, stability, and repeatability. Let's begin with the data. The S&P 500 is the main benchmark index for the US equity market, representing the majority of US large-cap companies and capturing shifts in sentiment, liquidity, and macro conditions. Predicting whether the market is calm, normal, turbulent, or in crisis is not just academic. It affects tactical allocation, hedging, leverage decisions, and stress testing. Many asset managers use regime models to dynamically adjust volatility targets, manage exposures, or detect when their models might enter unstable zones. We use 17 daily features such as returns, volatility, the volatility index, and other indicators. You see the feature list on the screen. They were chosen to capture price direction, uncertainty, risk appetite, and momentum, the fundamental drivers of market phases. Here is the historical distribution of the four regimes since 2010. Blue represents crisis or stress, red is correction, yellow is sideways or normal, and green is calm bull. Even from this long-range view, you can see clusters, transitions, and a clear imbalance. Crisis periods are shorter, but much more important for risk control. Regimes shift quickly, so here are two zoom-ins. In 2011 and 2012, the US downgrade and the euro crisis pushed markets through fast swings between stress and brief recoveries. Sudden spikes in volatility and rapid sentiment flips make this a textbook regime shift environment. And in late 2018, growth worries and tighter financial conditions triggered a rapid sell-off, showing how a stable phase can turn into turbulence within days. These examples illustrate why regime models matter. Misclassification can lead to wrong exposure at exactly the wrong time. Now that we have seen how the data is structured and the regimes are defined, we can look at the models. This slide shows how the two networks are built and why the comparison is fair. Both networks start from the same 17 engineered features. and apply the same pre-processing, scaling, and dimensionality reduction. The classical model remains fully in PyTorch, while the hybrid model replaces the central bottleneck layer with an 8-qubit variational quantum circuit built in PennyLane. Why 8 units? It mirrors the classical bottleneck size to keep both networks comparable and forces both models to compress information into the same latent space. The circuit depth is deliberately shallow to respect real hardware limits and to avoid unrealistic claims. After the quantum layer, both networks return to an identical post-processing stage that maps the 8 latent units to the 4 market regimes. Because every aspect, like data, splits, scaling, training loop, and metrics, is shared, any differences you see later come purely from this one architectural change. A fair comparison of classical versus hybrid. And, as always, the Jupyter Notebook is on www.qubit-lab.ch. Now let's train both networks. The chart shows how the classical and hybrid models learn over 100 epochs. The classical network reaches a slightly lower validation loss and shows a small mid-training plateau, which is normal and often caused by mini-batch noise or temporary flat regions in the loss landscape. A lower loss is interesting but not decisive. Classification quality will be measured through accuracy, F1, and per-class recall. Here is the row-normalized confusion matrix for the classical model. Row-normalized means each row sums to 1, so you can see how the model distributes predictions for a given true class. Diagonal values represent correct decisions. The classical model performs strongly on R0, R1, and R2, with only small spillovers into neighboring classes. The biggest challenge is R3, the stress regime, where some observations get misclassified as R2, a common issue in turbulent market phases where volatility indicators overlap. Here is the hybrid model. The diagonal is again strong for R0, R1 and R2, and spillovers remain small. The overall structure looks similar to the classical one. The delta confusion matrix shows where the hybrid differs. Positive values mean the hybrid assigns more samples to that predicted class. The differences are small across the board. Accuracy and F1 show slight improvements, with delta AC around plus 0.17% and delta F1 around plus 0.48%, exactly the scale you expect from a shallow hybrid model in a noisy real-world dataset. This schematic view summarizes our seed 0 run. Global metrics show only tiny gains. Class-wise recall shifts a bit, small positives in R0, R2 and R3, and a small drop in R1. To test stability, we repeat the entire process with a different random seed. Both networks rely on stochastic initialization and stochastic gradient updates, so different seeds create different optimization paths and can lead to noticeably different outcomes, a well-known phenomenon in ML research. So, we set the seed to 42 and redo the entire process. Comparing both seeds side by side, the pattern shifts. Some earlier gains flip sign, and the magnitude of deltas moves to different classes. This is completely normal. Each initialization explores a different region of parameter space. The important point is that the scale of the deltas stays small across seeds. When we evaluate a quantum model, we estimate an expectation value through repeated measurements. There is a true underlying value, but individual samples fluctuate around it due to inherent randomness. The animation shows this. The true value remains fixed while measured samples scatter around it. In practice, we never see the true value directly. We only observe samples. We compute their average and then estimate how precise this average is using a confidence interval. The more samples we gather, the narrower this interval becomes. The same principle applies to evaluating ML models. Each training run is one measurement of model performance, slightly noisy, slightly different. By repeating runs, we can estimate a stable underlying performance level. So we repeat the experiment 60 times. Each run yields a delta accuracy, delta F1, and 4 delta recalls. Together, they form 6 distributions. The histograms show how these deltas vary along with the Gaussian fit. The dashed blue line marks the mean, and the red dotted lines show the 95% confidence interval. This allows us to reason statistically rather than relying on single runs. We now understand how repeated measurements give us a mean value and a confidence interval for the true mean. The question we must answer next is whether a delta greater than 0 represents a statistically meaningful improvement, or whether it could still be explained by random variation. To do so, we proceed by assuming the opposite of what we want to show. We assume that the hybrid network is not better than the classical one. In other words, we assume that the true mean delta is exactly 0. This becomes our null hypothesis. Then we train the models with many seeds and measure the deltas. We calculate the measured mean and determine the confidence interval that reflects our uncertainty about the true underlying mean. If this confidence interval contains 0, then the null hypothesis stands. There is no evidence for a hybrid advantage. If, on the other hand, the entire confidence interval lies above 0, we must reject the null hypothesis. In that case, we have demonstrated a real hybrid advantage. Here are the mean delta values across all 61 runs, together with their confidence intervals. Each blue dot is the average improvement for that metric. The light blue band shows our measurement uncertainty. The green badges indicate metrics where the confidence interval is entirely above 0, a genuine and repeatable improvement. R2 recall shows a clear positive effect, but the standout result is R3 recall. R3 is the stress scenario, the most important regime in any risk-sensitive system. The hybrid model improves it by roughly 2 to 6 percentage points with high confidence. For crisis detection, volatility spikes, stress testing frameworks, and regime-aware portfolio management, this improvement is not small. Even a few percentage points more correct identification of stress phases can meaningfully change hedging behavior and downside protection. The orange boxes mark metrics that are slightly positive but statistically inconclusive. With more runs, they might sharpen, but based on our current sample, they remain in the maybe zone. The red boxes show no improvement. Confidence intervals include 0 or even lean slightly negative. Across all 61 runs, we end up with 3 groups. 2 metrics with no improvement, 2 uncertain, and 2 with a statistically confirmed gain. The most important of these is R3 recall, the regime where it matters most. So we found a significant improvement for R3 recall using a hybrid quantum architecture compared to a classical one. And remember, significant does not mean big. It simply means the improvement is statistically reliable and repeatable, even if the effect itself is small. That is it for today. Thank you for watching and for exploring this experiment with me. If you found it useful or have ideas for improvements, please leave a comment on YouTube or on the qubit-lab webpage. All code and resources are available at www.qubit-lab.ch. And one more thing. The first viewers who send insightful comments or critiques will receive an official qubit-lab coffee cup. So share your thoughts, challenge my findings, tell me what to test next, and maybe enjoy your next coffee in proper quantum style.